So this is the second lecture in the module on quantum mechanics, and here we will be discussing linear vector spaces. And what we will be doing here is first starting with a physical example and trying to understand the basic ideas and generalize it before we get to the actual mathematical definition of linear vector spaces. And you should see something in common with your maths course as well. Okay, so we start with vectors in high school and things that you saw in PH 1010. And there are two operations on vectors that we'll focus on. The first one is the addition of vectors. And what does that mean? If you give me any two vectors u and v, I can add them to create a new vector, which we denote by u plus v. So we have a plus operation here, which denotes addition of vectors. Similarly, there's a second operation which we'll call multiplication by a real scalar or just scalar multiplication. So let a be a real number and u be a vector, then a times u is also a vector. So for instance, 2 times u is just a scaled version of u, minus u is just the, in terms of arrows, is reversing the arrow. Okay. So, but quite often we actually represented a vector as a column vector with 3 rows. And how did we do that? We first picked a basis. So here we are assuming that we have a basis ex cap, ey cap, and ez cap, and we expand this vector in that basis. So we have u1, u2, and u3 are the components. So what we can do is hide the basis vectors and just put the components u1, u2, u3 as a column vector or a 3 by 1 matrix. Okay, and all the entries are real. So what we will do now is we'll forget about the basis, choice, etc. and just focus on this column vector and call the set of all column vectors as R3. So it's right now it's a set R3 with 3 real entries. So now we will look at two generalizations of these vectors. And the first generalization is very easy, is to just to increase the number of rows. So we just consider a column vector with n rows, or it's sometimes called an n-tuple. Okay, and so u here would be u1, u2 up to un. So there are n rows, and each of these u's, u1, u2 up to un, are all real valued. And we'll form a set again of all these guys, and we'll just call them this set, we'll call them Rn. So R just tells you that the entries are real and there are n rows. And what we will do is we'll continue to call elements of this set as vectors, or sometimes if you want to emphasize that the entries are real, we'll just call them real vectors. The second generalization is to make the entries complex. So here what we had was u1, u2 up to un were all real, but now we are going to make them all complex, and such a set of all complex n-tuples, we'll call that Cn. Okay, and elements of this set are complex vectors. So we have already seen this in the previous lecture, and we saw that the set of polarization vectors of an EM wave is C2, because we could write that, if you remember, as E3, E1. It was a column vector with 2 entries, E3, E1, both of them being complex. So now we are ready to give an intuitive definition of a vector space, and we will see that Rn and Cn form 2 examples of that. So we'll give an intuitive definition. So let V denote a set of vectors and F denote the set of scalars, because I'll keep using F because I don't want to keep switching back between R and C. So I mean so for us F can mean R and C. We will later see that it could be something much more general. So at this point F is either R or C. So then we say that the set V, so we have a set and a set of scalars. Set V is a linear vector space over F if the following two operations exist. Now the first is addition of vectors. For all possible vectors u and v, we can create a new vector by adding them, and we denote this vector by u plus v, and this should also be in this set. Second operation that we have is multiplication by a scalar. Let a belong to f. It's not a real number, but it's just a scalar, There's a typo here, and u is a vector. U could be any vector. Then a times u is also a vector. So these two operations will not take you out of the set, but will give you another element in the set. So this is the key idea. So we have two different kinds of operations, and we can actually go ahead and combine these two operations and require the following condition, that if you give me any two vectors u and v, and any two scalars a and b, the combination au plus bv is also in the set. So very easy to check that Rn is a LVS over reals and Cn is a LVS over complex numbers. So LVS is just short form for linear vector space. Sometimes I may just use a vector space. Now we will look at the formal definition that I have taken from Hefferon. This I have given you a link in Moodle. I will also be giving a link in the problem set which will follow this lecture. So a vector space over F consists of a set V with two operations, plus, that is vector addition, and dot, which is scalar multiplication, such that for all u, v, and w, which belong to vectors which belong to V, and a, b, any scalars a and b, the following conditions hold. So there are 10 conditions. So we'll see first the ones which involve just addition. So closure, this is a very important property. Closure of addition. So if u and v are any two vectors, their sum also belongs to V. Commutativity, u plus v and v plus u, the order doesn't matter. Associativity of addition, u plus v plus w, you have this thing, it doesn't matter which way you do it. You first add u plus v and then add w, or first add u plus w. Oh, I messed up here. It should be add v plus w first and then add u to it. Okay, so I guess it's clear. There's a typo again, really sorry. I'll fix it when I upload the slides. And so that's associativity of addition. As you can see, these are kind of intuitively obvious properties, but if you have to be mathematically precise, we need to put all these things in. And of course, there is a zero vector which satisfies that you add it to any vector u, it gives the same vector. Okay, so that is the fourth property. And the fifth property is that for every u, there exists an additive inverse w such that u plus w equal to 0. Okay. So now let's look at key things. And so here we will keep using a dot, a dot u, dot to indicate just scalar multiplying the vector. So closure under scalar multiplication. So for any u and for any a which is a scalar, their product will also be an element of V. So 1 and 6 are very important properties. Then this kind of distributive law kind of thing. If you have here, we have a plus b operating on u. So we can do it two ways. So left hand side is where you add them first. We can add two scalars to get a new scalar and then multiply it. Or you can multiply a times u and b times u and add them in the vector space. So here the plus is vector space addition, and this is in the scalar. This plus is scalar addition. This is vector addition. Okay, a similar thing, it distributes a scalar multiplication over a sum distribute. So here you first, this plus here is vector addition, so you add u plus v and then multiply with the scalar a. Here what you're doing is you first multiply with a on both and then add. And similarly for product a b, here you can take the multiplication in the as scalars and then multiply with u, get the number and then multiply. That's equal to doing it sequentially. First b with u and then a with u. And then an important, again like I said, we have to be mathematically precise. So there is identity, which is the multiplicative identity in the scalars. So 1 times u is u. So these 10 properties give a formal definition of a linear vector space. So I mean, when you have to check things, it's useful to just not memorize this thing, but sit with these 10 conditions and check. Okay. So now what you have to do is verify that Rn and Cn satisfy all the 10 conditions that appear in the formal definition. Kind of tedious, but not so hard. And you will quickly see that the proof for Rn and Cn is identical, so it's enough to do one of them. And then quite often one writes a dot u not as, one drops the dot and writes just as au. Similarly, one just writes 0 in place of, the vector 0 for the 0 vector. But this is very important. The closure properties 1 and 6 are important, and are the first ones we want to verify when you're trying to show that some set is an LVS. So usually what happens is you construct a set and you want to ask whether it's a linear vector space. So what you do is you go back, and so you will try to first say, okay, I will give it some addition, vector addition I'll define on that set, and also scalar multiplication. And then the first thing to ask is if condition 1, additive closure, and this is closure under multiplication holds. These two are always key. Okay, and so here is an exercise after Hefferon. So I did it for reals, I'm just doing it for complex. So let x, y belong to C2 and B be the set of points satisfying x plus y equal to A. Okay, so now you're asked to show that only for A not equal to 0 we obtain a complex LVS. Okay, so you can go ahead and check how closure breaks down. Does the property 1 break down, or properties 6 break down, or both break down? So this is a very nice simple exercise. It will take you a couple of minutes. And another thing I have not mentioned here is there exist other choices for F that are not of interest in this course. In general, F can be any field, and if you want to know what a field is, see Hefferon. I think it's in chapter 2 appendix or something for its definition if you're interested. Okay, I think people in computer science will encounter other finite fields and things like that. Okay, and now that we have a definition of a linear vector space, we have two examples, Rn and Cn, and with these in mind, we can just go ahead and ask for additional things. So the idea, an important idea, is the idea of a subspace. Okay, so we know if you're given a set, you can think of a subset. Okay, so here we are just saying to let V be a linear vector space over F, and let W be a subset of V. Now the question is, if I just take some arbitrary subset of V, okay, will it be a vector space? Okay, so first thing is we want to make W into a vector space. So first step is to try to ask what is plus and dot, that is addition and scalar multiplication. We have to put that property onto W, but that follows because we know how to add vectors and multiply by scalars in V, so we can just transfer those operations from V to W. Now that we have the operations, we would like to ask, will W be a linear vector space? As I mentioned earlier, the key is to verify closure under vector addition and scalar multiplication. If both the closures hold, okay, claim, then we have an LVS. Okay, you can go back and see if all the other 8 other conditions hold. Okay, that is an exercise for you to show that it holds. Okay, then we then say that W, we use the same notation as subset over V, but we read this as W is a subspace of V. Okay, that means W is a subset and it's also a linear vector space by itself. Now if W is a proper, that means W is smaller, there are elements in V which are not in W as a set, then we will call W a proper subspace. Okay, and if W equal to V, it is not a proper subspace. Okay, so this symbol here says not equal to, subset not equal to. Okay, so now let's do an example again. Consider a plane monochromatic EM wave with wave vector k, and let W be the set of complex vectors in C3 such that epsilon dot k, this is the usual dot product which we have seen, equal to 0. Then W is a subset, actually it's not equal to C3. So W is just a subset of C3. It's a subspace, it's a proper subspace of C3. Okay, and there is also one more trivial vector space, and that's the set containing just one element, a 0 vector. Okay, again it's very easy to check that all the axioms hold, and so it's a trivial subspace. An important point to remember is that if you give me any vector space, there are two sort of obvious subspaces. One is the trivial subspace, and the second one is the full space itself. Okay. So now we will go ahead and show how to construct a subspace from a set of vectors. So we start with S, which is a set of k vectors, u1, u2 to uk. Then what we do is we create a new set, which we'll call span of S, and that just consists of all vectors which are given by arbitrary linear combination of these k vectors. So these ai's, a1 to a2 to ak, are scalars, they belong to F. Okay, so it's obvious that by construction that we are obtaining in some sense the closure of these guys. So all elements which you can construct using these k vectors are elements of span S, and it's kind of more or less closure is obvious. So the other 8 you can check if you wish. It's easy to see the span S is a subspace of V. So we read span S as the span of the set S. Okay, so that means what we have done is you're given a set of vectors, and from that you're constructing a vector space. Now there are a couple of things you can ask. If you're given a set S, an interesting question is whether span S is a proper subspace of V or span S is equal to V. This is one question. Second question is, can two different set of vectors S and S prime be such that span of S is equal to span of S prime? So remember, we are starting with two different sets, but their spans are the same. So they are the same as vector spaces. And we will provide an affirmative answer next by an explicit construction. But of course, that won't be the only class of S primes that you can construct, but just to give an example. So now we come to an important idea which is called linear independence of vectors. So again, like before, let S be a set of k vectors in some vector space V. Then we say that the set of vectors are linearly independent if the only solution to the equation. What is this equation? It says take A1 is A1, A2 to AK are scalars. So A1 U1 plus A2 U2 plus up to AK UK equal to 0, and your goal is to find solutions A1, A2 to AK, these k scalars, such that this equation holds. There's always one trivial solution where all the A1s, AIs vanish. That is A1 equal to A2 equal to A3 equal to AK equal to 0. Okay. So, but if that is the only solution, then we say these k vectors are linearly independent. If there is a non-trivial solution, that means there are at least one or two of the, at least two or more of the A's are non-zero. Then the set is linearly dependent. So linearly independent means there's only a trivial solution, and linearly dependent means there is a non-trivial solution. Now suppose there is a non-trivial solution, and just to make things concrete, let's say A2 was non-zero. Then what we can do is you can just go to this equation, focus on A2, multiply this whole equation by A2 inverse. So what you get is a U2, and take the rest of the terms to the right hand side. So U2 can be written as minus A2 inverse times the sum of all the other elements except I not equal to 2. So it's just the same sum without the highlighted term. So what this tells you is that if the set is linearly dependent, we can eliminate one vector, in this case one of the vectors U2. We can write it in terms of all the other vectors. So U2 can be expressed as a linear combination of other vectors in the set S. Now we can do something. We can take S prime to be the set that you get after deleting U2 from S. So S prime has just, remember, S had k elements. Now we are deleting U2, so S prime has k minus 1 elements. It has one less element. But since U2 can be written in terms of all these vectors which lie in the S prime, span of S is nothing but equal to span of S prime. So this answers the second question that I raised some time back. Now we can go ahead and ask whether the set of vectors in S prime are linearly independent. If yes, let's rename S prime as SF. F for final. Okay, when final you will see why I'm calling it final. If no, you can, that means there is still one more non-trivial element. We can again eliminate one of the u's in terms of the other things, and we can keep doing this recursively until we finally arrive at a set SF which consists only of linearly independent elements. Every step of the way, this analog of this kind of equation holds. Okay, so at the end of the day, we'll see that span of SF is the same as the span of S, and F could be much smaller than S, because it depends on every step of this thing, number of elements reduced by 1. So if this is k elements, this will have some number of elements which might be less than or equal to k. But there is nothing unique about the set SF, because even coming back to here, instead of U2, so suppose A1 was non-zero, I could have eliminated U1 and got a different S prime. And so SF may not be unique. There are multiple choices that we can make. But one thing which remains the same is that the order of SF, that means the number of elements in SF, is always the same. You can prove this by contradiction. It's a fun thing. You can assume that and remember that span of SF, it doesn't matter how you start, they will all be the same they'll all be the same space. Okay, so you can prove this by contradiction by assuming that there are two different SFs with different elements which have the same span, and you will get a contradiction. Okay, so now we will go to an important idea, which again generalizes something which we know from usual vectors, is that there's something notion of a basis for an LBS. So a basis for V, so actually just one point here is that span of S, like I mentioned earlier, is that span of S could be a proper subspace or it could be all of V. Okay, so this is something which you can so we don't know this, so now in the case of a basis, span of the set, so B is a set of linearly independent vectors. So this is the analog of SF, but it satisfies span of B is V. So in other words, I get the full vector space. And the order of B, that means the number of elements of B, is called the dimension of B. Okay, several points are important. B is not going to be unique. But what is going to be unique is that not unique, right? Invariant is that the number or the order of the set B will be the same, and that's called the dimension of B. So a nice exercise. Both Rn and Cn are n-dimensional. That means I should give you a set B which has n linearly independent vectors. Okay, so here's what I'm going to do. E1, I'll write it as the first entry is 1, all the other entries are 0. E2, the second row is 1 and all the others are 0. Similarly, Ek would have the kth entry being 1 and all the others zeros, thus En as the last entry. And how many do we have? We have exactly n of them. And it's very easy exercise to prove that they are linearly independent. And I suggest you do it for some small thing like 3 or something, so that you see for yourself how it works. Okay, so this is the idea that there is a basis for V. That means if I have this basis, I can look at the span of the basis and I get all of V. In particular, the use of a basis is the following. Let V be a vector space of F of dimension n, and let B be given by n vectors, so E1, E2, En, they are linearly independent, remember, be a basis for V. And what does that tell you? If I go ahead and add any other vector into this, it will be linearly dependent on them. Why is that? Because already span B is V. So it can, in other words, you can get any vector in V can be written as a linear combination of elements in B. And that's what we are expressing here. It says U, which is an element of V of dimension n, will have U1, E1 plus U2, E2 plus so on and so forth, Un, En. Where U1, U2 up to Un, these coefficients are either real or F or complex depending on what F is. Okay. And again, now that we have a basis, we can write it as an n-tuple. Thus we see that any LBS of dimension n is isomorphic to either Rn or Cn. But the catch is we need to pick a basis and what comes in depends on the choice of basis. So we need to ask later, which we will answer this question. What will happen if someone else shows a second basis? How will they get related? This is something which we will discuss a little later. Okay, actually not little later, we're going to discuss it now. So the idea is how does a change of basis work? So the idea here is that let V be a vector space over F of dimension n, and let B be E1 to E2 to En be a basis for V, and this is just not repeated unnecessarily, and let B prime, which is E1 prime with basis vectors E1 prime, E2 prime, E1 prime, be a second basis for V. So we have two bases, B and B prime, and the question is how are the two bases related? So let's look at EI for some I. So let's say I take I to be 2 for instance, and then E2 is just some vector in V. So since B prime provides a basis, I can do an expansion. So I can expand this in the second basis. So I just write EI equal to summation Ej prime with some scalars. So the J runs from 1 to n. So Sji belongs to this. Okay, but I can write one such equation for E1, E2, E3, En. So what we have is n square numbers are sitting out here. And it's useful to think of this Sji as entries of a matrix. Okay, so the first index, remember, is always the row index. The second one is the column index. So here is this matrix S with entries S11, S12, S1n, so on and so forth up to Snn. So this matrix S captures how to go. If you give me something in the EI basis, I can write it in the EI prime basis. Okay, so we can also do the opposite. E prime for fixed I can be expanded in the basis B, not B prime, but I could have put a new matrix here, but again it turns out that it's just this has to be the inverse matrix, and the way to see that is you go back to this equation here, and so Ej you substitute here, and then you should get back you should basically get EI prime equal to EI prime. So you will require S inverse or S inverse S, rather it will be, let me look at that. Yeah, you will get something like S inverse equal should be identity, so that EI prime should be equal to EI prime. So just plug this in there. So this matrix, so the inverse of this matrix S appears in this thing. So it's very important that the matrix S be invertible, and thus its determinant S is not equal to 0. This is because both of them are basis vectors, and we know that these two matrices must exist. That means S is invertible. Now let's ask how the components of a vector change, because we have seen how the basis change is given. So this matrix S or S inverse tells you how to go back and forth between the two bases. Okay, the matrix S must be invertible. I've already said that. So let U be a vector with components Ui in the basis B and components Ui prime in the basis B prime. So what does that mean? U would be summation J equal to 1 Ej prime Uj prime. So Uj prime is the components in the basis B prime. Similarly, you can write it as summation Ei Ui, where Ui are the components in the basis B. But now we can go ahead and use this equation here, Ei equal to summation J equal to 1 Ej prime Sji. So I just put that in here. So that's what we have put here. This says I will just replace Ei with this thing. So now what we can do is collect terms. So this Ej prime, look at the coefficient of Ej prime on both sides, and we know that two vectors are equal if all their components are equal. That is a necessary and sufficient condition. So Uj prime will be equal to all these. The sum over I equal to 1 to n is Ji Ui. And now this has a very nice way of writing it. So you remember, we could write, once we have the two bases given, we can write them as complex, as column vectors. So it says U prime equal to S, the matrix S that was defined earlier, times U. So it just becomes matrix multiplication. Okay. So this is how, under a change of basis, we need to be given this matrix. It will tell you how to go from one basis to another. So now I'm nearing the end of my lecture, so we'll do some fun stuff, and we will enter the quantum world. Okay, it's a cheap entry into quantum world, but okay, just for fun, so that's okay. So the idea is that, let's say that you're given a set B with n elements, B1, B2 to Bn. What we will do now is we'll create a n-dimensional complex linear vector space from this set, and we will denote this linear vector space as C of B. We could have created a real vector space. I'll call that R of B. Okay, but I'm interested in complex, so I'll just call it complex. So to any set B, I can construct a vector space C of B. How do you do that? To each element Bi, you associate a basis vector Ei. Okay, so these E1 to E2 to En are assumed to be linearly independent, but this is by construction, and so you have this set of n vectors, one for each of these guys, and the span of that will give you a vector space. That vector space is what I call C of B. Now comes the interesting part. B1 plus B2 doesn't make sense, but E1 plus E2 makes sense. So we can add vectors, but we cannot add elements of a set. So that's one important this thing. And this, by the way, is a very standard trick in mathematics to prove certain things. I didn't know this, but it's also a way to understand quantum mechanics, as we will see. So we will start with some folklore stuff. So let B be equal to A and D. A for me means Schrodinger's cat is alive, and D means Schrodinger's cat is dead. In the classical world, there are only two possibilities, A or D. Now comes what happens in the quantum world. In the quantum world, the quantum state is a vector in C of B. It's not this thing. Okay, this is something which we will establish in this course. But now we have a nice construction. So what we have is a vector space, and in particular, and now I'll just call this EA is the basis vector with A, and ED is the basis vector due to D. So because I can add these guys, let's just, I mean, this is just for 1 over root 2 is not so important at this point, but I'm just putting it for things which will, when we come back to this, 1 upon root 2 times EA plus ED. So what we have is a linear superposition of A and D. So in the quantum mechanical state, the cat can be both alive or dead and dead. So these are some keywords which you should understand after this lecture. If you don't, please go back and listen to the lecture or work through the problem set. Now I'll end my lecture by making a kind of controversial statement. Since all LVSs are isomorphic to Rn or Cn, does that make them boring? Okay. And just some facts. Problem set 12 will be uploaded on Moodle and will be based on the last two lectures, that is lecture 4 and 5. And in the next lecture, we will study maps between vector spaces as well as additional structure. We'll add additional structure to whatever we have defined today for LVS. The additional structure is really length of a vector or inner product.